So, hello everyone. Today we would like to talk about our neighbors. So, the topic is contending with the neighbors, moons, asteroids, comets, and impacts. So, this is the course introduction to geochemistry. So, first of all, I think some of you still remember your high school experience when your earth science teacher talk about moons. It's always painstaking because they start to talk about tides and how to calculate different tidal phases, which is usually very complicated. But overall, we should indeed care about our neighbors. That is our moon. Why? Because as oceanographic undergraduate, I think many of you know that our moon is one of the forces that drives tides, like high tides, low tides. This image show the formation mechanism of tides. So because nowadays the tidal level is not very high, so tide seems to be a very unnoticeable phenomena. However, based on one of my physical oceanographic colleague, he said that actually in coastal environments, tides are actually the most important physical oceanographic forces that you should pay attention to. That was a video clip of Interstellar, the giant wave scene. So if I remember correctly, the wave was actually generated by the tide. And you might think that was very exaggerated. However, as a planet with oceanic water, we should definitely care about our moon because it will definitely influence the behavior of tides. Physics told us that there is a phenomena called tidal friction. It means when the moon is rotating around the Earth, there will be a gradual energy transfer from Earth's spin to the moon. So the consequence of tidal friction is the Earth's spin will slow down, the moon's spin will speed up. And most importantly, moon will gradually move away from the Earth. And based on measurement, scientists have determined that today the rate is 4 centimeters per year. That is actually quite phenomenal. If you apply the speed to back calculate what would happen to the moon in the past, scientists realized that in Earth's early history, there were actually more lunar cycles per year, so that actually means the tidal wave will move much faster than it is today. In coral records, scientists already found evidence for much shorter lunar tidal periods. Like in several million years ago, the lunar cycle might be twice as fast as it is today. Furthermore, the tides were actually much greater, and if there were animals looking into the sky, they would find that the moon is twice as large as it is now in the night sky. In other words, that means what was depicted in Interstellar is not totally unimaginable. In fact, it could have happened in the ancient Earth. Take a look of today's tidal range. It's usually less than 5 meters. The only exception is the Bay of Fundy. It has the most extreme tidal range up to 17 meters. However, according to scientists, the ancient tidal range may be 3 times higher than it is today and with a shorter tidal period. So that means faster tidal wave and higher tidal wave. It's almost like what was depicted in Interstellar. So based on these phenomena, I think we should definitely pay a little attention to our quiet but influential neighbor, the moon. Let's take a look of these small neighbors in the solar system. There's actually a diverse array of objects in the solar system. Our solar system contains one star, the sun, 8 planets, and we have actually more than 150 moons, or we can call them satellites, or 100 billion asteroids, and 1,000 billion comets. There are actually many small objects, and these smaller planetary objects are actually affecting the Earth in different ways, so they are not negligible. In fact, I think most of you should know that the extinction of dinosaurs has been now attributed to the impact of an extraterrestrial object. Here is a visualization of satellites of the solar system. So you see this is the major moons of Jupiter, and for Saturn, so we have in previous lecture we have talked about Titan when we talk about Cassini-Huygens mission. Uranus also have several moons, and then Neptune. And this is the size of Earth's moon, which is just a little bit smaller than Mercury. So look at this. And then please recall what you have learned from the lecture of planetary system. So what are the similarities between the planet-satellite system and the solar system? Take a look and think a little bit. So look at this, especially the Saturn, and look at the relative size of the moon. From this diagram, we can say that, first of all, these planet-satellite systems, they pretty much follow the same distribution of the star-planet system. For example, if this is the star, this is the planet, you can see that they are basically coplanar. In previous lecture in the planetary system, we call this ecliptic. You can see that there seems to be also something like an ecliptic for the Saturn. In the case of Saturn, the moon closer to the planets, they are smaller in size, while the moon at a more distant place from the planets have larger size. So it's also pretty much like the solar system. And furthermore, many of these moons, they are actually in a prograde motion. Prograde. So we will talk about this here. The modal motion. Prograde in Chinese is called 顺行,顺利的顺,顺行. So that means the satellite orbits in the same direction as the rotation of the planet. So if the planet is rotating clockwise, then the satellite or the moon also orbit clockwise. That usually means the satellite is formed in the gravity field of a planet as a planet is forming. They are within the same gravity field and probably of the same source material. However, there's also moon in the mode of retrograde motion. So retrograde in Chinese, we call it 逆行. It means if the planet is rotating in clockwise direction, then the moon is in counterclockwise direction. That usually means the satellite is actually formed elsewhere, and later it was captured into the orbit by a planet's gravity. So it was actually formed elsewhere and then maybe ejected from its original place into the solar system and then was captured by this planet. However, I need to here say that a captured satellite can have either a prograde or a retrograde orbit. If you see a moon in the prograde motion, that doesn't necessarily mean that it's formed in the same gravity field. So it could be also a captured moon. We know that moons or satellites, they have very different appearance, like we see Europa, Io, Callisto, Ganymede. So these are the moon of Jupiter. And of course, we should take a look of our moon, our dear neighbor. So we know that moon has a near side and a far side. And this is the side that we usually look at. There are shade on the moon. We call it lunar Maria. And lunar highlands are the brighter part of the moon. Another thing we immediately notice is that on the moon, there are many craters. Craters are common features of satellite, like this. And most craters on satellites, they are actually circular, like this one. However, what would be the force to create a round-shaped depression? Is that reasonable? We might think, why not? But however, you can imagine that you are now throwing a baseball, and then the baseball fall on the ground. Can you imagine that this depression caused by the baseball that you threw out, would it be in a circular shape or would it be in an elliptical shape, 椭圆形或圆形? Okay, I think you would guess it would not be in a circular shape. This is because low-angle impacts should lead to elliptical craters, not circular ones. On Earth, there are actually several forces that would create circular depressions, like volcanism. So this is a volcanic crater. And usually you can find very perfect circular shape if it's a volcanic crater. Or other forces would also include glaciers. So if there were glaciers here, the weight of glacier would also result in some depression that would look like a crater, and this would usually in a circular shape. Then, how did scientists determine that these circular craters on satellites, they were indeed from impacts? Basically, this was based on numerical modelings. Numerical modeling demonstrated that impacting objects traveling at hypervelocity, that means 17 to 70 kilometers per second, can generate shock waves, 冲击波. And it is the shock rather than the impact object itself that creates a circular crater. This diagram shows the formation of an impact crater. Originally, an impact object is in contact with the ground, and then it will create this shock wave, and this shock wave will propagate along the ground, and then it will produce a very special thing called ejecta, like here. And then with the propagation of the shock wave, the ejecta will actually expand. And at the end, it is the ejecta that created this circular shape. And usually, if it is an impact crater, you can find the remnants of ejecta at the surrounding of the crater. Like here, you might be able to find some special chemical signature in the ejecta that can prove that this is an impact crater. And in addition, within the crater, you can also find some special minerals or compounds that can indicate that this is an impact crater. So what could be the substance that can best indicate that the crater you find here is an impact crater instead of a volcanic or glacial crater? So scientists have discovered that these two compounds are considered definite evidence of an impact origin. One is called stishovite, and the other is tektite. So we will talk about them. So this is stishovite. Stishovite is actually also SiO2. So in fact, its chemical formula is exactly the same as quartz. This is quartz. We have talked about quartz in our lecture, Mineral Chemistry. We know quartz, and also most of the silicates on Earth is made of tetrahedron. Okay, like the drum here is made of tetrahedron. However, how can we know that stishovite is not regular, normal silicates found on Earth? Because stishovite is made of silicate octahedron. That's very unusual, right? And furthermore, we know that all silicate can be dissolved in hydrogen fluoride. Okay, that's what the semiconductor factory use in the etching process. However, stishovite is the rare silicate which is resistant to hydrogen fluoride. So that makes it very, very special. And it's only formed under this high pressure condition of impact events. So stishovite is the first good indication of an impact event. And the second is tektite. Tektite in Chinese called 雷公火, 雷公火. This is the tektite. So you can see that it looks like a little bit like a volcanic glass. So it doesn't look like a crystal. Furthermore, very often it has these teardrop shape, 泪珠状的, teardrop shaped. Sometimes you can find them under microscope. So if any of you are working on marine sediment, maybe you can pay attention. If you see structure like this, so you see this is also glassy, 像玻璃一样. However, it has this teardrop shape, and it has a very small size of a few hundred micrometer. Then they might be the so-called microtektite. This kind of microtektites or tektites, they were produced during past impact events, and they can have very broad spatial distribution. Like, for example, here around us, there is a very large area like this, the number 7 area, where we know we can find tektites or microtektites in marine sediments. One of my previous colleagues, when I was doing my master thesis, he is now a professor in one university in Taiwan. His PhD thesis actually worked on the microtektites found in the Indian Ocean and link this to impact events. That means that's something you could really find in marine sediments. It's not something that's very remote from you. So we now know that the craters on moons are usually impact craters. So what are the sources of impacting objects? Where are they from? The first source is very close to the Earth. What is it? You have to remind yourself what you have heard from our lecture, Planetary Systems. There is an area where it is considered a failed planet. What is it? It is the asteroid belt, 小行星带. In astronomy, they usually call these near-Earth objects, NEO. So these are asteroids with Earth-crossing orbits. That means this source is very close to us. So take a look. This is Earth. This is the asteroid belt. So you see, in fact, our living environments in the universe or in the solar system is not as safe as we imagined, because these small objects here, with some disturbance of the gravity field, any of them can be ejected into the inner solar system. And the second is the Kuiper belt. It is a belt of asteroids beyond the orbit of Neptune, with Pluto being the largest representative. So you know that some scientists think Pluto is not a planet. In concordance with this idea, Pluto is considered a larger asteroid in the outer solar system, the Kuiper belt here. And the last one is the Oort cloud. Oort cloud. It is a hypothesized spherical cloud containing solar system debris. It defines the cosmographical boundary of the solar system. You can recall the lecture about the solar system, where we know that the solar wind and also the orbit of the gas giant like the Jupiter and Saturn, they will wipe away the small debris from the strictly defined solar system. Therefore, at the exterior of the solar system, scientists hypothesize that there is actually a spherical cloud like this, and they believe that these are the homeland of most comets here. It comprising many billions of comets, and these are the so-called the many billions of comets I mentioned in my earlier slides, so in the Oort clouds. So these comets, they have a more remote home from us. Below are some important facts of the impacting objects. So the decisive factor for an object to have Earth-crossing orbits is the gravitational influence of nearby planets. What would be the nearby planets? Take a look. What are the planets that are affecting objects in the asteroid belt and the Kuiper belts? I would like to answer this using this cartoon. So this is the sun. This is us. It says, hey, watch where you're throwing those asteroids. This is the asteroid belt. And who is doing that? Jupiter. Jupiter is the bad guy. Because with some small variation in its orbit, it can disturb the nearby smaller objects and make it ejected elsewhere. And this asteroid belt, as mentioned, is closer to us. So we are more likely to be influenced by this. As for Kuiper belt, the nearby planet is Neptune. This is the second bad guy who is also affecting us. Second, important fact. Impacts arise from materials whose orbits have been recently perturbed. Although you might think, based on the advancement of astronomy, we would be able to predict maybe the orbits of or whatever extraterrestrial objects for the next 100 years. You might have this imagination, but in fact, this is not always the case. For example, when I was junior high school student, there was a very big astronomic event. It's a comet called Shoemaker-Levy. At that time, it's a very big event. It's a comet that collided with Jupiter in July 1994. When I was a little kid, I would think, this is something that astronomers knew long time ago, maybe half a century ago. However, this comet was discovered only 16 months before the impact. 16 months. Imagine if today this comet collides not with Jupiter but with Earth and is a very large comet or asteroid with only a prediction time of 16 months. Would that be enough to build a spaceship like the movie 2012 depicted? Probably not, right? So it's actually something that's recently perturbed. These are the two important facts. So now it will be time for us to take a deeper look of our nearest neighbor, our dearest moon. If you take a look of the planet-satellite relationship in the solar system, then you will realize that the Earth-Moon system is somewhat peculiar. That means 有点怪怪的. Typically, the satellite-planet mass ratio is very small. For example, in our previous slide, we show Ganymede. Its mass ratio to Jupiter is very small, 8 times 10 to the minus 5. And for Titan, which we have seen in previous lecture, the video regarding Cassini-Huygens, its mass ratio to Saturn is 2 times 10 to the minus 4. For other two cases, they are both very small. However, for our moon Earth, the mass ratio is only 1%. In other words, our moon is remarkably heavy as a satellite. You might think, these are Jupiter, Saturn, Uranus, Neptune. These are probably all outer solar system. However, even if we only look at the inner system, Earth is the only inner planet with a satellite of significant size. As said, our moon is just slightly smaller than Mercury. The second weird thing is the moon has a low density compared to other inner solar system bodies. These are the inner solar system bodies. If you recall what we said regarding the planetary systems, we talk about density. The inner solar system bodies, they generally have density around 5,000 kilogram per cubic meter. However, this is not the case for the moon, which has only a density of 3,300. That is relatively small, right? Below are more things regarding the peculiar Earth-Moon system. So now I will read through The moon is not even like the Earth in every aspect. That means it's probably not produced in the same gravity field or not produced from the same source material. First of all, as shown here, it has a very density from the Earth. And then its low density suggests that the moon doesn't have a core, or the core is very, very small. The Earth has an iron core, right? But the moon probably doesn't have a core. It is depleted in siderophile element. If you recall the lecture regarding interior segregation, we talk about different philes like a siderophile, trichophile, etc. So siderophile means the element has a higher preference to stay with metal, right? However, here it says it is depleted in stereophile elements. That means based on the material the astronomer retrieved from the moon, so you know that they got this material from the surface of the moon, this rock is poor in stereophile elements. That means it is depleted in elements that favor to stay with metal. If you see this, you probably would think, okay, if you don't find these siderophile elements in the outer surface of the moon, you probably can find them at the interior of the moon. In other words, if you look at these results and you might think maybe the moon shares the same structure as the Earth, then you might think, okay, if I don't find siderophile elements in the surface, then we probably find it in a core, and then that would probably infer that the moon should have a core. However, the density doesn't support this possibility. So that means this observation and this observation, they don't agree with each other. Scientists also found that the moon is very depleted in volatile elements compared to the Earth. They measure the abundance of stable oxygen isotope, oxygen 16, 17, and 18 of the moon's silicates. You know that it's not just foraminifera or water that you can measure oxygen isotope. We know that silicate is made of silica and oxygen. So you can also measure the oxygen isotope of silicates. You can measure the isotope of silicates on moon and on the Earth, and then you can compare them. If they are made from the same source material, then they are likely to share the same isotopic signature. They found that the abundance, the stable isotopy ratio of moon silicate is identical to that of the Earth. That means the Earth and the moon, they have a common parentage. And another thing is the age of the moon's oldest material is 4.4 billion years ago. And it is actually a little bit older than the oldest material that can be found on Earth. Is about 50 million years older than the Earth. So we talked about the Earth's age in our previous lecture about the principles of radioactive dating. How to explain all these peculiarity? There are several hypotheses that have been put forward to explain the origin of the moon. The first is the so-called capture hypothesis. The moon accreted in an orbit close to the Earth and was finally captured to enter the orbit around the Earth. Okay, in other words, that's the so-called captured celestial object that I mentioned in previous slide. But what would be the problem for this hypothesis? It fails to explain, first, why there's no lunar core. If it's accreted in an orbit close to the Earth, that would probably mean that because for most of the inner planets, they all have a core. If the moon is also accreted in the inner solar system, it's very likely that it will also have a core because we know that the moon, our moon, is relatively large. It's only slightly smaller than Mercury. But we don't see a lunar core based on the density. Furthermore, it is actually difficult for the Earth to catch such a big object without touching it. So it's very unlikely to be a smooth process. The second theory is the fission theory, fission hypothesis. The moon formed by fission from Earth after Earth's core had formed. what does that really mean? And what are the problems of this theory? The hypothesis actually is telling us that first, the Earth's interior has segregated. So we know, we talked about this in our previous lecture, that the segregation of the Earth's interior happened quickly. And then the fission hypothesis that said that after the segregation has completed, somehow the outer part of the Earth is separated from the Earth to form the moon. So what could be the mechanism for this separation? The mechanism proposed to support the hypothesis is by spinning. In order for such separation to happen, it requires that the Earth had to spin extremely fast. It's like you spin and spin, then you can throw away the outermost part of your material. But you have to spin very, very fast. How fast? You need to spin at a rate that can complete a day in 2 hours. Okay, that means 12 times faster than it is now. It is faster than observed elsewhere in the solar system. So in other words, in solar system, you never find any object spinning in such a high speed. This is extremely fast. If it is indeed formed by fission from Earth after Earth's core has formed, it fails to explain why the slightly older age of the moon. The last and the most accepted hypothesis is giant impact hypothesis. So the hypothesis states that another planet, which is about the size of Mars, collided with the Earth. The ejecta, so you learn this word when we talk about shock wave, okay, about impact. The ejecta spread around the joint planets and condensed to form the moon. This hypothesis is mainly confirmed by numerical modeling. However, this hypothesis can explain most of the lunar puzzles that I mentioned in previous slides. That's the reason that makes it the most widely accepted hypothesis. So in fact, last year, NASA just published a simulation done by supercomputer about how the moon might have been formed during this giant impact. So let's take a look. Since the Apollo mission, so we now have real physical samples from the moon. The mission brought back lunar materials for a total of 390 kilograms, and the samples provide important insights into the evolution of the moon. So now we want to talk about several aspects of, or several results that were made based on the samples of the Apollo mission. So the first thing is we want to know the mineral composition of moon rocks. So we know that this is the lunar highlands, and the dark part is the lunar Maria. The material brought back from the Apollo mission told us that the lunar highlands and Maria, they were made of different minerals, or they were made of different rocks. The highlands were made of anorthosite with a density of 3.7, and Maria was made of basalt with a density of 3.0. And below is a detailed mineral composition of these two types of rock. So anorthosite is primarily made of anorthite. Anorthosite is the name of a rock, and northite is the name of mineral. So this is the chemical formula of anorthite. You can see that anorthite alone is made of 90% of this rock. So this is quite unusual because on Earth, you probably barely find a rock with such a single monomineralic composition. So only made of one single material, because here is up to 90%. For basalt, it has more balanced contribution from plagioclase and pyroxene. It's most monomineralic. What does that mean? If you recall the lecture where we talk about partial dissolution, you can realize that actually for the rock on Earth, it's barely that they would have monomineralic composition. So we will come back to this later. The second thing is we want to talk about an important family of elements in earth sciences, rare earth elements, in short, or the abbreviation is REE. REE. So REE basically referred to lanthanides. So these are lanthanides. So you see they are here in this row of the periodic table. They all have a Xeon core. Xeon core here. This is a electron configuration of Xeon. This is the valence shell of each lanthanide elements. You don't need to remember this. All lanthanides, they tend to form trivalent. That means this, trivalent cations. And these trivalent cations differ only in inner shell electron numbers. For example, let's now look at europium. This is the electron configuration of europium. When it forms a trivalent cation, it needs to lose 3 electrons, right? So it will throw away first the 6s2, and then it needs to throw away 1 electron from 4f, right? So it will have 4f6. So that's what it said, the inner shell electron numbers. So you see these cations, they differ in the orbital of 4f with different numbers. So now I have a question. How does the ionic size change with proton numbers? So here we have increasing proton numbers. Would the size become larger with increasing proton number or smaller with increasing proton number? So you need to recall what we talked about in the lecture of mineral chemistry. So the answer is the ionic radii of lanthanide cations will decrease with increasing atomic number like this. So this is in the order of increasing proton number, and this is ionic radius. So you see that it decreases with increasing proton number. This is because of the higher proton density in the nucleus. They are mostly trivalent. That means they have constant charge, but they have different size, ionic radius. This is important for isomorphous substitution. What is that? Please again refer to our lecture of mineral chemistry. However, europium is a special one. Europium has 2 valence states, europium 2+ and europium 3+. Let's look at previous slide. Europium, this is a trivalent electron configuration. In this orbital, it has 4 of 6. If it's europium 2+, it will be 4 of F7. Let's take a look of this diagram. I think some scientists probably call it spider diagram. Very often in application involving REE, they will present the whole series of REE, present in this diagram, like a spider diagram. Here, this is in increasing proton number. And here, they compare the concentration of REE in lunar rock with something else. Can you get what would they compare to if they want to know that whether the lunar rock is relatively enriched or relatively depleted in specific REE elements? What would they compare? The scientists choose to compare with chondrite. Chondrite, because we learned from a previous lecture that chondrites have been considered to be representative of undifferentiated solar system material. So they compare this with chondrite. And they figure out that for lunar, the highland anorthosite, and for the lunar Maria, the basalt, they have different europium anomalies. In the lunar anorthosite, europium is specifically enriched. So this is compared to the general trend of concentration in the rock material. So this is relatively enriched, while in lunar Maria, the basalt, the European is relatively depleted. It gives people the impression that the European has moved from the lunar basalt to the lunar anorthosite. Here is some mineralogical explanation for this enrichment. So we know that anorthosite is mainly made of anorthite, the mineral. And this is a chemical formula of anorthite, which has this cation, calcium. And we know that in this chemical formula, calcium is bivalent. And we know European has valence states of 2+. So European can substitute calcium in anorthite. And we know that in anorthite, the most abundant mineral is what? It's a kind of plagioclase. This is the general formula of plagioclase, which could be either sodium or calcium. And then if it's mainly calcium, this mineral is called anorthite. Here, the lunar basalt may have experienced some sort of plagioclase removal. That basically means anorthite removal. This makes people wonder whether this enrichment and this depletion, they are mutually related to each other. Now we talk about the third one, the radioactive dating. So in my previous slide, I already talked about the age of lunar rocks is slightly older than the oldest rock on Earth. But how did they obtain the dates? Apparently, they need material from the moon. Here, they use an isotope pair involving samarium-147, which decays to neodymium-143. This is the alpha decay, which has a half-life of 106 billion years. As mentioned in our previous lecture regarding radioactive dating technique, we need this radioactive nuclide samarium-147. We also need this daughter 143, neodymium. However, we also need a stable isotope, which is neodymium-144 here. By looking for the different minerals from the plagioclase or from the mafics, which involves the mineral pyroxene or olivine, they could make this isochrone. Isochrone, I hope you still remember the definition of isochrone. Using the slope and the half-life, they can calculate the age of moon rocks. That's how I read this graph. In this figure, this is from the lunar anorthosite. So we know that in lunar anorthosite, it has the mineral plagioclase, which is the most abundant part one, but it also has pyroxene and olivine. So let's take a look, right? It has minor trace amount of pyroxene and trace amount of olivine. So the age here will represent the age of anorthosite, which is 4.45 or 46 billion years ago. The scientists also did more detailed dating of the moon rock because I already mentioned that on the moon, they are both lunar Maria basalt and lunar highland anorthosite. These are different material. And here, they specifically dated Apollo 15 basalt from the lunar Maria. And this is the result. We look at this graph here. So these are different samples, I think. However, from both samples, they obtained an age of 3.1 to 3.7 billion years, and using the same isotope pairs, samarium and neodymium. The lunar Maria basalt are younger than the lunar highland anorthosite. That's a key message here. So how to explain this mineralogical, the REE, or the dating result? Here is a scenario proposed to explain all this. The scenario is the lunar magma ocean. It is proposed that after the impact of a Mars-like object with the Earth, the moon was created and accreted. at the beginning, the moon at the surface was actually completely molten magma ocean. And why? Because of the heat from the impact. So it's completely molten. And then what happened is, during cool down, the anorthosite paleoglass will crystallize first. After it crystallizes, because it might have lower density than basalt, as you see, its density is 2.7 instead of 3 of basalt, it will float at the top of the magma ocean. This is the reason why we see this monomineralic rock. You can imagine that the anorthosite is extracting europium from the magma below it. It extracted europium because anorthosite contains calcium in its chemical formula. Therefore, the solidified anorthosite has a positive europium anomaly, while the remaining magma has a negative europium anomaly. And then the moon experienced a short period of magma activity and extrusion. Why? Because here so far, the remaining magma here should be buried below the anorthosite. However, right now at the moon, we see the lunar Maria. Because it's exposed to the surface of the moon, that means it has extruded. 就是已经出露到月球地表上了。So that means at that time, the moon might have some magmatic activity like our volcanic activity. The volcanic activity brought the magma to the surface of the moon and left the basaltic rock exposed there. And because this happened slightly later than the anorthosite solidification, so there is age difference between the highland and Maria. After explaining the peculiarity of the moon and also the results, the finding based on the Apollo mission, now we want to talk about the early impact history of the solar system. This is the Earth, very beautiful, very blue. And this is the moon with a lot of crater. The moon is full of crater, while the Earth has few in today's surface. Is it simply because we are more lucky than the moon? When some asteroids or comets came and hit the moon, it will simply bypass the Earth? Are we simply that lucky? Of course not. There are a few more facts relating to this question. Are we luckier? We know that the oldest rock on Earth date 3.9 billion years. That's the oldest rock. But the moon dated back to 4.5 or 4.45 billion years. Based on the previous scenario or hypothesis, the moon should have originated from the Earth. It's probably part of the previous crust and mantle because the density is comparable, about 3. So the Earth should be as old as the moon. But what happened between 4.5 billion years and 3.9 billion years on Earth? Why couldn't we find any rock older than 3.9 billion years on Earth? Why? We need to note that because the moon is relatively small, its mass is 1% of the Earth. So the moon has no modern volcanism. And there's no atmosphere to produce weathering. And today has no tectonic movement to wipe out all rocks. As we mentioned in the principles of radioactive dating, when we want to date a material, the material needs to be a closed system. Okay, a closed system. However, in terms of rock, what can make it an open system? It's very easy. If the rock is involved in the volcanic cycle, 火成循环, then the rock is no longer a closed system. Once it's melted, its system is open again to the surrounding. So the moon, you can consider it as a planetary fossil that records events in Earth's vicinity in very ancient time. Because it doesn't have volcanic and tectonic activity, so it doesn't wipe out old rocks, and because it doesn't have weathering, the crater is now wiped out by surface processes. So it's a fossil. Because the Apollo mission brought back these impact breccias, so the deposit around the impact craters, scientists could do dating on these impact breccias, and then they found that the impact breccia had a date of about 3.9 to 3.8 billion years ago, so younger than the lunar highlands. So the relative age constraint can also be obtained by looking at the geological relationship of the craters. Like, if you look at this one should be formed first, and then you see this smaller crater overlapping the larger one. So this smaller crater should be younger. So that's what the textbook meant by looking at the geological relationship of craters. By studying the planetary fossil or moon, scientists came up with this figure. So in this figure, this is the age or time. You can think of it as time because we know that the solar system started 4.6 billion years ago, and this is the impact mass flux. So how did they come up with this estimate? We need some hypothesis. So the hypothesis is there is an exponential decay of impact rates. And then we can constrain the exponential decay with some available numbers, like we have today's impact rates, because we know today the Earth is still receiving meteorites, asteroids, comets, so we have impact rates. We also know the impact rates on the moon. We also know that. However, they figure out that around 3.9 to 3.8 billion years ago, the cratering intensity increased remarkably, like this. So it's like an anomalous period of the solar system where we have very high impact mass flux, okay, at least for the Earth and the moon. So this period has a specific name called the late heavy bombardment. Why does it called late? This is compared to the initial state of the solar system where we think there must be a lot of impact events in order to accrete the planets. So at the beginning of the solar system, there must be a high impact mass flux. You can call it early heavy bombardment, and this is late heavy bombardment. There is explanation for the LHB, late heavy bombardment. That is the gas giant migration. Gas giant refers to the Jupiter and the Saturn. You know, because their mass is very big, a small change in their orbit will affect many other smaller celestial objects. This is the hypothesized orbits before gas giant migration is hypothesized. And then the Jupiter and Saturn migrated. They changed their orbit. Why? I don't know. And then, because of that, as I just mentioned, because the Jupiter, especially Jupiter, is very close to the asteroid belt, asteroid perturbed and ejected into the solar system. And later, Jupiter and Saturn, they reach 2-to-1 resonance in their orbits. The interplanetary space is also largely cleared, okay, based on what we talked about in the lecture of planetary system. This gas giant migration is believed or proposed to be the explanation for the late heavy bombardment. What does that mean for the Earth? As I mentioned earlier, the rocks dated older than 3.9 billion years ago are very rare on Earth. This could be a natural consequence of late heavy bombardment, because with this heavy bombardment, older rocks might have been wiped out because of so many bombardment. And the oldest fossil on Earth dated 3.5 billion years ago, or 0.4 billion years after the late heavy bombardment. Does that mean before the late heavy bombardment there was no life? Not necessarily. But it's very likely that if any life was present before the late heavy bombardment, it was wiped out by the impacts. Because the impact at that time might be very, very intense, enough to extinct any living creature on Earth. Therefore, the oldest fossil dated 3.5 billion years. This could be due to an ease of surface sterilization caused by heavy impacts. That's the implication for the Earth. I hope that after today's lecture, you would appreciate that today our moon, its tidal cycle, its tidal range is already much more comfortable for us. Because imagine if you need to experience this such intense tidal range and also such short tidal cycle on the ocean when you go to a research cruise. I don't think anyone can really work on the ocean because the tidal range could be so large, like what you see in the video clip of Interstellar. We appreciate our Earth, and we also appreciate that it helps us, it maintains some ancient record of the impact events. And I hope that next time when you think about our moon, it's not just mythology, but also think about its past and how its record provides implication for the life and the history of the Earth.